Hello, we are going to do 8.2.2 all in one lesson today, so I am warning you the video is a bit longer, but we are not splitting it up, and if you notice we're only doing 8.2.2 and 8.2.3 this week, so you only have 3 actual lessons, which is nice. So we're going to get started looking back at complex roots. Now if you remember last week, we learned that imaginary numbers are used when we take square roots of negatives, and we said we need to memorize that I is equivalent to the square root of -1. That's something we need to memorize, and also that I squared is equivalent to -1. Okay, so these ideas, these tools are going to be used this week as we start to work more with complex numbers, which complex roots, complex numbers always implies imaginary. So as our introduction, in this lesson you will solve equations as well as reverse your thinking to investigate the relationship between complex solutions and quadratic equations and the equation from which the solution came from. Okay, so the first thing that we're going to do on 79 is we are going to find the roots. Now, roots are x-intercepts. You've got to know that. Okay, for each of the following quadratic functions, and they're giving us a lot more information than we really need. They're saying, okay, solve for x when y is 0. Well, yes, that's what an x-intercept is. And then we're being asked, after you find the solutions, do the solutions tell us then that the function is going to intersect the x-axis? So let's go ahead and just first find those roots, those x-intercepts. So when I replace y with 0, okay, so I'm replacing y with 0 here. Then I know I'm going to solve by undoing because this is in graphing form. So I'm going to subtract 9 from each side. So 0 minus 9 is -9. So I have -9 equals x plus 5 quantity squared. Okay, now from here to undo the square, we are going to square root both sides, and we know that when we're solving an equation, we have to consider the plus or minus case. So we have plus or minus square root of -9 equals x plus 5. All right, so we see that that -9 is going to create an imaginary number because normally we'd say, wait, we can't go any further because we can't square root a negative. Okay, but let's first solve for x and then take care of using our I and I squared up here. So if I solve for x, I need to subtract 5 from both sides. So when I subtract 5 from both sides, I'm going to put that out front because that's my real component. So I have -5 plus or minus the square root of -9 is x. Okay, so we solved for x, but now what we want to do is we always want to get rid of the negative under the square root by using this up here. Okay, so what we are going to do, my scratch work, I'm not going to do this on every problem, but remember we can split up -9 into the square root of 9 and the square root of -1. Okay, what is the square root of -1? I. What's the square root of 9? 3. So 3i is what we are going to replace the square root of -9 with. So our solution, our roots to the quadratic equation are -5 plus or minus 3i. Now remember the shortcut I said, when you see a square root of a negative, take the square root of a number, ignoring the negative, and then just tack the I on. Okay, so we can see that this is a complex number because it has an imaginary component. So are these going to show up on the graph? No. Okay, we can see that this will not intersect the x-axis because of the complex root, the I component. Okay, now on this next one, we can see that this is not in graphing form, this is in standard form, so we need to approach it slightly differently, and because I don't want to take a chance, I'm going to use the quadratic formula. So I'm going to do x equals the opposite of b, which is 4 plus or minus the square root of -4 squared minus 4 times 1 times 9, 4ac, all over 2 times a, which is 1. Okay, when we simplify under the square root, we get x equals 4 plus or minus the square root of 16 minus 36 over 2. So what does that result in? We have 4 plus or minus 16 minus 36 is negative 20 over 2. So what is this going to be? This is going to result in complex roots. Okay, so when I go ahead and do this, I am going to say, oh, well, 20 is not a perfect square number. So what can I break 20 into? I can break 20 into the square root of negative 1, the square root of 4, and the square root of 5. So you have to look for those factors. 4 times 5 times negative 1 is 20. Why did I do this? Because I'm trying to find perfect square numbers that I can break down. So I know the square root of negative 1 is I, the square root of 4 is 2, so I'm going to write 2I, but then I have to keep the square root of 5. Because I can't square root that, it's going to be an irrational number and I do not want to round. So when I go back to my quadratic formula, I have 4 plus or minus 2I times root 5, okay? That's the same thing as the square root of negative 20 over 2. And now I'm going to divide each component by 2. So 4 divided by 2 is 2. And 2 divided by 2 is 1, so I get 2 plus I root 5. I don't think I'm going to have space there. Let's see, equals 2 plus I root 5, and it should be plus or minus. 2 plus or minus. So these are the roots of the original problem. So again, this is not going to intersect the x-axis because both of these equations involve complex roots, not real roots. So you will not be able to see any x-intercepts. All right, so what we are going to do is on 81, we're going to do an exploration that leads to patterns. And what we're going to calculate is the sum and the product for each pair of complex numbers. Now remember, complex numbers have the real component and the imaginary component. And then we're going to use our patterns to answer some further questions and make our life a little easier. Now on these, I think you should watch me do one, try to pause me, and try to do some of the others, and then just kind of fast forward to check your answers. Okay, so that's a way to make this video a little less tedious if you start to catch on. Okay, so if we're going to find the sum, for the sum, we are taking 2 plus I plus 2 minus I. Now, because we just have a plus sign, we can ignore the parentheses. So we're going to combine our like terms. So I plus negative I actually gets to just cross out. Thank goodness. And then 2 plus 2 is 4. So the sum is plain old 4. That cleaned up nicely. Okay. And then now for the product, okay, we are going to have to kind of use our knowledge of double distributing because we are taking 2 plus I times 2 minus I, and now we have to distribute that first 2. So 2 times 2 is 4, 2 times negative I is negative 2I, and then I times 2 is positive 2I, and then I times negative I is negative I squared. So now we have to use our knowledge of I and I squared to clean things up as well as do some canceling out because negative 2I plus 2I cross each other out. They're opposites. So now I'm left with 4 minus, what did we say I squared is? I squared can always be replaced with negative 1. But be careful with that double negative. The double negative makes a plus. So the product of those two complex numbers makes a real number. Very interesting. Okay, moving right along. Now for this next one, I am asked to find the sum. I'm not going to write out the full expression because I'm just adding the two things so I can move terms around. So I see that negative 5i plus 5i cancels out. And then if I take 3 plus 3, my sum is 6. Okay, now for the product. With the product, I have to double distribute. Be very careful there. So I have 3 minus 5i. I have 3 plus 5i. And then I'm going to distribute my first 3. So 3 times 3 is 9. 3 times 5i. Treat it I like a variable when you do the arithmetic. So I have 15i. And then I have negative 5 times 3 is negative 15i. And then I have negative 5 times positive 5. So negative 25i times I is I squared. Once again, I notice a pattern that my I terms drop out. And I have 9 minus 25, and what is I squared? It's negative 1. So when I do the math, I have 9 plus 25, which is 34. So once again, the product of those two complex imaginary numbers ends up being a real number. Try these two next ones on your own, and then see if you match my answers. So for the sum, I see that positive I plus negative I is going to cancel out. And then negative 4 plus negative 4 is negative 8. So the sum of those two numbers is negative 8. And then when I move to the product, I'm going to take negative 4 plus I, negative 4 minus I, see what happens, distribute that negative 4. So I have 16, positive 16 plus 4i because the double negative. Then I have negative 4i. And I have negative I squared. So then, yay, my middle terms cross out. So I have 16 minus negative 1. The negatives make a positive, so I get 17. All right, continuing on. Try this last one. So we have, the square roots might seem scary, but let's go through the same process. So for the sum, I'm thinking 1 plus I root 3 plus quantity 1 minus I root 3, but that plus sign doesn't do anything in terms of distributing, so I can leave the parentheses out and focus on combining like terms. Well, the good news is I root 3 minus I root 3 cancels out, so those don't need to cause us any fear, and then 1 plus 1 is 2. So the sum of the numbers is 2. And then if I go ahead and look at the product, let's write it out and think about distributing. So 1 plus I root 3 times 1 minus I root 3. Okay, so let's see. 1 times 1 is 1. 1 times negative I root 3 is negative I root 3. I root 3 times 1 is positive I root 3. And then I root 3 times negative I root 3. Let's be careful here. I times negative I is negative I squared. And then what's any root times itself? Root 3 times root 3, the thing underneath pops out, so it's 3. So this is 3I squared, negative 3I squared. So when I combine some like terms, yay, still my I terms cross out, so I have 1 minus, what's I squared? It's negative 1, and I still have to have that 3. So this, we've got to be careful, but if I take negative 1 times 3, that's negative 3, but then I have a double negative, so I have 1 plus 3, which is 4. Okay. So now it's time for patterns. Okay, so when we are asked on E, sorry, I'm changing my papers around. On E it says, okay, use the patterns that you found and make a good conjecture. What complex number can I multiply this by so that I get a real number as my result? Well, hopefully if you look back at A through D, I keep my same real component, but then I do the opposite of the imaginary component. That is the pattern we wanted you to catch on to. Okay, now if you look at F, is F like what we just did on A through D? It says negative 4 plus 5i, but then it says negative 4 plus 3i. They kept the same real component, but the imaginary components are not opposites. So we can see that because the imaginary components are not opposites, maybe it's not going to be as nice. Okay, so when we go ahead and do our double distributing, Okay, I have negative 4 times negative 4 is 16. Then I have negative 4 times 3i is negative 12i. Then I have 5i times negative 4 is negative 20i. And then 5i times 3i is 15i squared. What happens with my i's? They do not cancel out. So I have 16 minus 32i, because I just add them together. They're like terms. And then what's 15i squared? It's really 15 times negative 1. So I have negative 15. I'm substituting I squared. So then when I take 16 minus 15, I get 1 minus 32i. So what do we notice here? This is another complex number. So what happens? We get another complex number. So please keep in mind that when you multiply two complex numbers, you do not always get a real number like we did up here. Okay? So the moral of the story is, when will we get a real number? Okay? What complex number can you multiply something of this form to get a real number? Well, we can multiply it by what we're going to call the conjugate. Okay, the conjugate in complex numbers is the same real component, A stands for a real number, minus bi. It's the opposite of the imaginary component. Okay, so this would be a real number, and b would also be a number, but this is considered the imaginary component. Okay, so the moral of the story is a plus bi times a minus bi is going to result in a real number because the imaginary components are opposite. This is the key idea of this entire lesson. Okay, so now we are going to focus more on quadratics, roots, x-intercepts. Okay, so each of the four pairs on A through D could be the roots of a quadratic function. Okay, because quadratic functions use real numbers, but then the roots are imaginary if it doesn't cross the x-axis. So what we are going to do is create a quadratic equation for the pairs of complex numbers on A through D. Okay, so what we're going to do is think back to what we did in the first section of this chapter, and it says Austin's thinking that if he knew, for instance, that 3 and negative 5 were the solutions of a quadratic equation, then in reverse he could say the factors are x minus 3 and x plus 5. Remember doing that a week or two ago with polynomials, and you reviewed that just yesterday on your worksheet. Okay, so how could we use this idea when we know, though, that the roots are complex solutions? So we are going to start with looking at what we're going to call problem A, okay? And if you recall, these were given as the roots, okay? So if these are the x-intercepts, they're complex, we're not going to be able to see them on a graph, but what would the factors be? Okay, well, the factors, you've got to be careful, we're going to use brackets and take it slow, are going to be the opposite of each. So we're going to take x, and what does opposite mean in math? Minus. So x minus 2 plus I, and then we're going to take x minus the quantity, and you've got to put that quantity in parentheses because we're going to do some distributing. Okay, so we're doing exactly what we did with the polynomials, but it looks scary because we have these i's occurring. But the first step is you're always just going to take the minus and put your complex number paired with the x. All right, so also this should be, you can keep your a, but I need space. So y equals, because we're creating a quadratic function. Now what we're going to do is we are going to make sure to be careful with this minus, distribute it through. So we have x minus 2 minus I, and then we have x minus 2 plus I. Okay, now what we need to do, this is the tedious part, yikes, is we are going to go ahead and double distribute, I guess, triple distribute, whatever you want to call it, because we have to take x times all three numbers. So we have x squared minus 2x plus xi, okay? And then we have, distribute the 2, we have negative 2x plus 4 minus 2i. And then finally, we have, distribute the I, we have negative xi plus 2i minus I squared. You have to be very careful to not make any mistakes, but some way to keep yourself on track is we should see things drop out. So first of all, I am going to look and I see that I have my positive xi and my negative xi. Okay, I have my positive 2i, I have my negative 2i. Now I'm going to combine like terms, so negative 2x makes negative 4x, okay, and then I have plus 4, and then what's negative, or what's I squared? Negative 1. So now, look, my imaginary component completely went away. So when I combine, I get that my quadratic function x squared minus 4x plus 5 would produce these roots right here, okay? They are complex roots, so it would not have x-intercepts. So we just worked the process backwards. All right. Okay, so now what we want to do is we want to continue this on for some more problems. So let's go ahead and get started. Again, pause me if you've caught on. There's no reason to watch me through it all, but check your answers. So if we are trying to find a quadratic equation that has these as the roots, we are going to go ahead and say y equals x minus, use that double parenthesis, 3 minus 5i. And then we have x minus 3 plus 5i. Okay, so we need to double distribute. Or no, sorry, we need to simplify. We need to distribute that negative. So x minus 3 plus 5i, distribute the negative, and then distribute the negative again. X minus 3 minus 5i. Okay, then we're going to do a lot of distributing. So I'm going to first distribute my x. So I have y equals x squared minus 3x minus 5xi. Now I'm going to distribute my negative 3. So I have negative 3x plus 9 plus 15i. Then I'm going to distribute my 5i. So I have positive 5xi minus 15i, and then minus 25i squared. Now I'm going to look and see that things cancel out. So I have negative 5xi and 5xi. I have 15i and negative 15i. So I have y equals x squared minus 6x. Combine your like terms. I have plus 9, and then I have minus 25, and I squared's negative 1. So, finally, I get y equals x squared minus 6x, and then positive 25 plus 9 is 34. Whoops. So we can see that this quadratic equation that consists of all real numbers produces complex roots because the parabola, the graph would not cross the x-axis. Okay, keep going. So now on this next one, we have y equals x minus 4, negative 4, plus I. And then we have times, make our opposite root, x minus negative 4 minus I. Got to be careful with all those negatives. So now we're going to distribute. So we have x plus 4 minus I. That's our first factor. And then we have x plus 4 plus I. And now we're going to do a lot of distributing starting with this x. So we have y equals x squared plus 4x plus xi. And then we have this 4 to be distributed, so plus 4x plus 16 plus 4i. And then we have this negative I, so we have negative xi minus 4i, and then minus I squared. So we are going to look to cross things out. We have negative xi, positive xi. We have positive 4i, negative 4i. So y equals x squared plus 8x, and then plus 16 minus negative 1. So y equals x squared plus 8x plus 17 is the quadratic equation. That if you would use the quadratic formula and you would go through the quadratic formula, guess what you would get as your answer? What we started with. Okay, that's what we're doing to try to reinforce that. Now the final one where we all get scared with the square roots, but it's the same process. So we have y equals the quantity x minus quantity 1 plus I root 3. And then we have x minus the quantity 1 minus I root 3. Okay, distribute your negative. So we have x minus 1 minus I root 3. And then we have x minus 1 minus plus I root 3. Okay, now we need to do our distributing. So distribute the x first. Y equals x squared minus x plus xi root 3. Okay, now negative 1, negative x plus 1 minus I root 3. Now negative I root 3, so negative xi root 3 plus I root 3, and then be careful here. Negative I times I is negative I squared, but then root 3 times root 3 is 3, so we have minus 3. Let's see here, minus 3i squared. Sorry, I'm just reordering those a little bit. And now we're going to go ahead and do some canceling out. So we have, let's see, xi root 3, negative xi root 3, negative I root 3, I root 3. So we have y equals x squared minus 2x, and then plus 1, and then minus 3 times negative 1. So we have x squared minus 2x, and then plus 1 plus 3. So our final quadratic that would give these original, what we started with as the roots, is x squared minus 2x plus 4. Whew! Hopefully you have caught on to that process, because that is 4 what I would call drill problems. Okay, so now what we are going to do is, it says for each pair of numbers below, find a quadratic equation that has these numbers as solutions. Okay, same process, but now they're mixing it up. Again, pause me and try these problems. Practice makes perfect. But on this first one, we're given real roots. So we would just do y equals x minus 3/4, and then we do x, you could just do minus negative 5, but we learned with the polynomials that you can just say x plus 5. Okay, just showing you where that relates. So we have x, I'm going to rewrite it so that it's easier to look at. X plus 5. So then now, we want to go ahead and write it in standard form. So what are we going to do? We are going to go ahead and double distribute to make it look nice. So we can go ahead and first go with the x. So we get y equals x squared plus 5x, and then now negative 3/4. So we have negative 3/4 x. And then let's see, minus 15 force. Okay, so that is going to be, let's see, we can combine our like terms. Sorry, I am looking at something and questioning myself. So you're going to see some people not want to deal with fractions, so I'm going to actually backtrack. You could just simply get out your calculator and do your fractions, but I'm going to bring back fraction busters and think about, okay, if I look at this factor right here, okay, do you agree with me that this factor is the same thing? If I multiply everything by 4, that this factor is the same thing as 4x minus 3. Okay, think about it. If I had the factor 4x minus 3 and I use ZPP and set it equal to 0 and I solved, I'd add 3 and divide by 4. What would that give me? The root I started with. Why do I consider wanting 4x minus 3? Because then I don't have to work with fractions. Okay, now this won't be assessed from you, but I do feel like I want to show you how to make things nice and clean. Okay, so I'm going to go ahead, instead of working with fractions, and work with this new factored form. So I'm going to have y equals 4x squared plus 20x minus 3x minus 15. Makes my life a lot easier, not worrying about fractions. 4x squared plus 17x minus 15. Okay. And notice that it says find a quadratic equation. So basically we just need to know that both of these factors would create a root of 3/4. So either student would be correct based on whichever one you wanted to use. Now, back to our imaginary component. So we have y equals, we have to do x minus 3i, and then we have x minus negative 3i. So we have x minus 3i, and then really it makes x plus 3i. Ooh, I like this. So then distribute your x first. So x times x is x squared plus 3xi, and then distribute your negative 3i, so negative 3ix, and then minus 9i squared. So we now have these cross out, and we get y equals x squared and then minus 9 times negative 1. So y equals x squared plus 9 is our quadratic that, if you use quadratic formula, would give these complex numbers as the roots. 2 more. Keep working hard. Okay, now we are going to look at making a quadratic out of this complex number. So x minus 5 plus 2i, and then we have x minus 5 minus 2i. So y equals, clean things up with distributing, negative 5 minus 2i, and then we have x minus 5 plus 2i. Now we're going to do lots of distributing starting with the x. So y equals x squared minus 5x plus 2xi. And then we have negative 5x plus 25. And then minus 10i. And then we have negative 2i. So we have negative 2xi plus 10i. And then minus 4i squared. Yikes. Okay, so hopefully lots of things will cancel out. So we have 2xi, negative 2xi. Then we have negative 10i and 10i. So now let's combine our like terms. We get y equals x squared minus 10x, and then plus 25 minus 4 times, replace I with that negative 1. So negative 4 times negative 1 is positive 4. So if we combine like terms, I get x squared minus 10x and then plus 29. So this would give you these roots if you performed the quadratic formula and simplified the complex number when you found the negative under the square root. One more, try it on your own, see if you can get it right. Y equals x minus negative 3 plus root 2. And then we have x minus negative 3 minus root 2. We can be confident that we're going to end up with a real number because they're conjugates. So, distribute your negative. x plus 3 minus root 2, x plus 3, let's see, x plus 3 plus root 2. All right, from here, we are going to distribute starting with the x, so y equals x squared plus 3x plus x root 2. And then I'm going to distribute the 3, and so I have plus 3x, and then plus 9, and then plus 3 root 2, and then distribute the negative root 2, so I have negative x root 2, and then I have negative 3 root 2, and negative root 2 times root 2 pops out the 2, so we have negative 2. Okay. These were not complex numbers to begin with, though. These were irrational numbers, but you're going to notice that it kind of works the same way. So we have x root 2, negative x root 2. We have 3 root 2, negative 3 root 2. So now I get y equals x squared plus 6x, and then 9 minus 2 is 7. So we can see, okay, that this quadratic equation does indeed have real roots, but we notice that these real roots are irrational. Okay, they're going to be nasty decimal numbers, so they're irrational. But what happened when we took two irrational roots? It created just a real a real quadratic equation that had rational coefficients. Very interesting. Thanks for hanging with me. Like I said, we took one lesson, did it in one day, so you only have one more lesson to do. After you do your homework, keep working hard. There's a light at the end of the tunnel, and we'll talk to you next lesson.